Hello, Chem team. Here are some initial notes on acid-base theory in general chemistry. Okay, so I'm going to, so again, these notes will be posted to you. So here I'm just going to annotate along and say some things that might come to mind. Okay, so acid-base theory, some definitions. What is an acid and a base? So we have a couple of definitions here. Some are more useful and more general than others. So first off, we have the Arrhenius definition of an acid and a base from the Swedish scientist Svante Arrhenius, same Arrhenius from the Arrhenius equation. So this was, to give you an idea when this was being formulated, it was around 1910-ish. So basically, Svante Arrhenius said that an acid is anything that produces, accumulates protons in solution, and a base is anything that accumulates hydroxide ions in solution. So when I say proton, I mean H+, as seen here, and obviously hydroxide is OH-. Now, the OH- is stable in solution. The H+ is not stable in solution. So the H+ will actually interact with a water molecule if it's in a watery environment, and it will form hydronium ion, which is H3O+, but we'll see that in a second. An example of an Arrhenius acid is hydrochloric acid. And as we can see here, hydrochloric acid, when it's in an aqueous environment, it's a strong acid, so it will completely dissociate into its constituent ions. So we have a unidirectional arrow, and you'll have H+ and Cl-. So HCl is clearly an Arrhenius acid because it produces H+ in solution. Sodium hydroxide is an Arrhenius base. It's a strong base. It completely dissociates in solution. And when we see here, we have sodium hydroxide in a solution, and it will actually exist as free ions. So the free ions are going to be Na+ and OH-, so clearly we've produced hydroxide ions in solution. Remember from earlier classes, some language here. So when we say completely dissociates or a strong acid and base, we mean forms free ions, completely forms free ions as the predominant species. And these ions are also known as electrolytes. So electrolytes down here. Maybe I can get my pointer. There's a way I can have a pointer, I guess. Spotlight, yes. No? Yes. Okay, there we go. So we've got electrolytes down here. That just means ions. So we can say that HCl and NaOH are strong acids and base respectively. They are strong electrolytes. The predominant species are the free ions. So these are all ways of saying the same thing. Okay. So hydrogen ions are what we said earlier are protons. So we know that a proton is a subatomic particle, but in acid-base chemistry, a proton is literally the unshielded proton from a hydrogen atom, or just H+. So think of a hydrogen atom or a protium isotope of hydrogen with just one proton without its electron. So it's an exposed, unprotected proton. But as we said earlier, a proton by itself, or hydrogen ion, is not stable. It will be ravaged by a water molecule to give a hydronium ion, which is the stable form of the proton. Some textbooks or some people will use protons. Some better people will use hydronium ions, and we are the latter. And if ever you have material that has proton, you can just convert it to the better, more realistic form, the hydronium ion, just by adding a water molecule. So that's a way to quickly fix the lack thereof. Okay. And the hydronium ion is how the proton would exist in nature in a watery solution environment. Okay. All right, so I'm going to turn the next page in my notes. Okay, so on this page, we're looking at dissociation, and we're going to start to introduce predominant species, but much more on that in another video. So you can tell an acid in the box because if the Arrhenius acid produces H plus in solution, it must have H plus as a cation. So therefore, if we write formulas with cations on the left, which we do, then you would expect to have H to the leftmost side of your chemical formula. So HCl clearly has an H, and as we said earlier, that's a strong Arrhenius acid. If we look at HCl, actually put it into some water, you can see it will in fact make its hydronium ion and Cl minus, and you can see the relationship between these two equations. The top equation, we're just looking at the dissociation of the ions. The bottom one is a lot more realistic because it will dissociate into liquid water. So both equations say the same thing. The bottom equation says it in a better way. If we look at what we have though, well, actually, no. Okay, so let's say we have just on the text given on the left, we just have dissociation of the strong acid. What if we were to mix the strong acid with a strong base? What if we were to do a neutralization reaction? So here we're looking at an acid and a base. Maybe I can write on this actually. Let's try and mess the flow up by writing on it. So this would be a neutralization. Where by neutralization, I mean we have an acid plus a base to give a salt and water. Okay. So if we have something like that, let's go back to the spotlight again. Okay. Then we've got our acid, which is the predominant species from HCl. So we've got hydronium and Cl. That's the predominant species. I've mitigated aqueous label, but it's clear that it's aqueous because they're ionic. More about that later. So we've got the principal species of HCl, and then I've got a strong base, the principal species of potassium hydroxide, so it's its free ions. We would get water because the hydronium is going to unite with the hydroxide to give us 2 molecules of water. And then the K is going to unite with the Cl, but that's just a strong electrolyte anyway, so it will remain as its free ions. Because it remains as free ions, the Cl minus and the K plus will cancel on both sides. So maybe we can do that. The Cl minus and the K plus will cancel as spectators on both sides. And we're left with just hydronium and hydroxide, which are over here, and 2 lots of water on the right as the predominant species. So we can see that what's actually happening when we do a neutralization in solution is we're just making water molecules. Assuming that we're not going to destroy water, as long as we're within the activation energy range of water synthesis, then we're not going to destroy water, we can just make water. Okay. So let's go back to scrolling mode. Oh, so I have to actually clear my drawings, otherwise it won't let me scroll properly. Okay. But if you need them, obviously you can go back in the video. So that's for strong acids and bases that dissociate 100% in water. What about weak acids and bases that only partially or incompletely dissociate? So we're told here weak acids do not ionize completely, which is indicated by the use of an equilibrium arrow. So we've got our equilibrium arrows as opposed to our lack thereof for the strong system. Now, HF is a weak acid. Unlike HCl, HF is a weak acid. And that means that it itself is the predominant species. So when we write on a piece of paper for somebody to see, hey, this is an acid, it's a proton donor, it produces protons in solution, which would eventually form hydronium ions in solution. That's true, but because it's weak, we know that the acid dissociation constant, or Ka, must be less than 1. So its equilibrium is shifted onto the left side. It favors reactants. So whatever's favored is the predominant species. So it would be misleading to write H plus and F minus for a weak acid HF. We would just say it's HF aqueous. Okay, so they are the predominant species. That's where the vast majority of the molecules are shifted to. Let's look at the neutralization. So we already looked at neutralization with a strong acid and a strong base, and we saw predominant species were water molecules. In fact, specifically, this predominant species is the water molecule. And I should really catch this. So the predominant species is actually just water. It's not hydronium and hydroxide. For reasons that we'll talk about later, it's because of the Kw value being very, very large. But the predominant species is just water molecules. So let's look at the predominant species for the weak system. So let's say we have HF and the strong base, KOH. So we've got a weak acid and a strong base. We have to look at predominant species. So the predominant species for the weak acid is just HF because it only partially dissociates. However, the predominant species for the strong base are the free ions because it completely dissociates. So now you can really see what's happening. I've got HF with these free ions. And I know that I'm going to have a double displacement or a neutralization. So I'm going to form water and KF. Well, KF is a strong electrolyte. It's a salt, but it's also a strong electrolyte, so it will completely dissociate. And we have water. So I can cancel K from both sides. That's a common strong electrolyte from both sides. And then I just rewrite what's left as the predominant species. So I'm left with HF. I'm left with hydroxide. And then I have F minus and water as my predominant species. And you can see it in the visual here. The strong acid and the weak acid system here. The strong acid completely dissociates as the predominant species are hydronium and Cl minus. The weak acid incompletely dissociates. So you can see here with HCl, these are the predominant species. Predominant species. But with a weak system HF, the intact HF is the predominant species. And that affects how you write it on a piece of paper. Okay, so scrolling on to the next page. Okay, so enough with the Arrhenius definition and how to write these things on paper. Let's look at arguably a more useful definition, at least for what we're going to do moving forward, the Bronsted-Lowry definition of acids and bases. So the Bronsted-Lowry definition builds upon the Arrhenius definition and came a little bit later, so about a decade later, so around 1923. And we're told that a Bronsted acid is a proton donor, where remember proton is H+, and a Bronsted base or a Bronsted-Lowry base is a proton acceptor. So here the proton, oh, I've got it here. The proton is H+, yeah. Okay. So Arrhenius, remember, said that you produce protons in solution. Bronsted says you are a proton donor. So almost the same thing, but from a slightly different perspective. Okay. And certainly you'll find the Bronsted-Lowry is the most versatile definition of the definitions we're going to see today and in this video. So the most common acid-base definitions in use today are certainly the Bronsted-Lowry definitions. Very useful in medical applications when you look at acid-base chemistry in metabolism, for example, and other biochemical regimes. We're going to start to look at how to think about Bronsted-Lowry acids, and there's definitely some vocab that's going to come up. We are going to look at some materials that can act as both a Bronsted-Lowry acid and a Bronsted-Lowry base, depending on circumstances. So just like an amphibian is an animal that can live on land and water equally, an amphoteric material is a material that can function as both an acid and a base, depending on circumstance. And if specifically, if the amphoteric material contains H+, then it can specifically be amphiprotic. If it can donate and accept H+, then it can be amphiprotic, which is a specific form of amphoterism. Okay, so there's going to be some vocab that we'll pick up as we go. Let's look at the conjugate system. So it will be quite common to write conjugate pairs in the Bronsted-Lowry regime of acid-base theory. So if we look at this equation here, so you've got acetic acid on the left, you put it in water, it is a weak acid. We know that because of the equilibrium arrows. So equilibrium is going to be shifted left. If ever you see equilibrium arrows, you can assume that K is less than 1. So I would say if you see equilibrium, let's write this down. It's not a rule, but I would say at least in my classes, so if you see equilibrium, you can assume K is less than 1. Again, I wouldn't say it's a rule, but it's a reasonable assumption, because if K is greater than 1, most people wouldn't bother to write the equilibrium. They would just have a single arrow. But you can have equilibrium shifted on the right. Anyway, so we have acetic acid and water to give hydronium and acetate anion. And a conjugate pair essentially is one member of the reactant with one member of the product. So it's literally a before and after shot. You know, you were a reactant on the left, what did you become on the right? And conjugate pairs, I don't know if I've annotated anywhere else. Yeah, I've actually annotated on the next page. They can only differ by 1 proton. So you know you've got a pair when the only difference between the 2 members of the pair is 1 H+. Anything more than 1 H+ difference, they're not a conjugate pair. So we can see here that the acetic acid, the only difference between this acid on the left and this base on the right is the extra H+. So we've lost the H and we've gained the negative charge. That's because we've lost the plus charge as well. So that's a conjugate pair. And then likewise in the middle for water, You've got oxygen has 2 protons. Now oxygen has a third proton with a plus charge. That's a difference of 1 H plus, so that's conjugate pair also. The one thing you will notice is we've now got a problem. We can see we have an acid and base on the reactant side and the product side. So now we have to give extra nomenclature to label the left and right. So if I say acid, it's not clear which one I mean. Do I mean acetic acid, far left, or do I mean hydronium, second most far right? Or if I say base, do I mean water or acetate? So by definition, if you are a reactant, you give the prefix Bronsted-Lowry. So this is the Bronsted-Lowry acid. I'm going to abbreviate BLA. This, therefore, is the Bronsted-Lowry base. Now, if you're a product, you're just a conjugate. So hydronium here is the conjugate acid, and acetate is the conjugate base. So out of definition, whenever we say conjugate acid or conjugate base, we always mean the products. Whenever we either just say acid or base, or in my classes at least, I'll always say Bronsted-Lowry acid or Bronsted-Lowry base, I always mean reactants. Okay. Notice that just like in math, if you transpose in math, which means go across the equal sign, you change the argument. So a multiplication on the left will become a division on the right, and addition on the left will become a subtraction on the right. Here, an acid on the left becomes a base on the right, and vice versa. So acids and bases are antitheses of each other. So if you're an acid on the left, your conjugate partner is going to be a base. If you're a base on the left, your conjugate pair is going to be an acid. So that's an important observation. Okay. So let us scroll. Okay. So yes, so I've annotated here where I meant by pair. A pair diff is only by plus or minus a proton. So we have to be careful about that. Not by any other charge, not by 2 protons, just by 1 proton. We can see here ammonia on the left, the N has 3 H's or 3 protons. On the right, its partner has an extra proton and its plus charge. That's a conjugate pair. Oxygen here has 2 protons on the left, 1 proton on the right. Now, in passing, notice that we had water here as an acid, but previously we had water as a base. Now, can anyone remember the vocab? Here we have water being able to act as an acid and a base at the same time. Then water can be amphoteric. Specifically, it's amphiprotic, but generally it's amphoteric. It can be an acid and base at the same time. Okay, so again, the Bronsted-Lowry built upon the Arrhenius ideas and came about a decade later, but definitely contemporary with the Arrhenius ideas. All Arrhenius acids are Bronsted-Lowry acids, and all Arrhenius bases are Bronsted-Lowry bases, but the return favor is not always true. And you won't really appreciate that till later on when we look at salts, but that will be in later acid-base theory videos when we look at the acid-base properties of different salts. But more on that later. And just remind ourselves of some vocab. Any compound capable of acting as both an acid and a base is amphoteric. When this action as acid and base involves donating and accepting protons, specifically, we say amphiprotic, where protic here means proton. Okay, what about the strength of acids and bases? We saw earlier in the Arrhenius definitions that we could have partial dissociation for a weak acid or base, complete dissociation for a strong acid or base. and we can have K values, a K value at an equilibrium constant value less than 1 tells us we have a weak system, a weak electrolyte, and a K value greater than 1 tells us we have a strong electrolyte. What else can we do? We can definitely do that again here, but specifically we're interested in the strengths of the acids, the Bronsted-Lowry acid versus the conjugate acid, or the Bronsted-Lowry base versus the conjugate base. Okay. So what do I want to say here? Okay. So whenever we say, well, first of all, I want to go back. Whenever we talk about a K value, so for example, I should have annotated up here. I have the argument. The argument here is the base. So I would say the way I think of it, at least, and that's the only way I can tell you, the argument of my sentence, to me, this is a sentence. Okay, this is the base sentence. The argument is the base, and it happens in water. So I would say, the way I think of it, water, the solvent here is the environment. So yes, I have an acid and a base, but my argument is a base. So therefore, I would have a base dissociation constant, which is NH4 plus OH minus. I ignore water because it's a liquid, and I have NH3. So I have a base argument. Now, the K value, the equilibrium dissociation constant value, is always with respect to the argument, which is always going to be a reactant. You're never going to have a K value that talks about the products. So K is always about the argument, which is always a reactant. Okay, so I want that to be clear before I erase it so I can scroll back. Now, having said that, when we talk about strength, we're going to look at the K value. You have to remember what it relates to. It relates to the argument, which is on the left. So if we look at a generic equation here, so I've got a generic expression, HA, which is a general acid, and water gives hydronium and conjugate base. So here's our argument. Here is our environment. So our argument is a Bronsted-Lowry acid. So clearly we have a Ka. So the environment is Bronsted-Lowry base, but that's not the argument. We wouldn't have a Kb for this expression. That's our conjugate acid. That's our conjugate base. Here's our conjugate pairs. You might wonder which is stronger, HA or hydronium, or BLB or water or A minus. So I think I spell it out on the next page. Let me just make sure I do. No, I don't. So I'm going to spell it out on this page. Okay, let's see if I can squeeze it in here somewhere. So if Ka is less than 1, the conjugates are stronger than the Bronsted-Lowrys. So if Ka is less than 1, in fact, I'll keep it general. You can just say if K. Here it's an acid specifically, but in general, I can just say, let me get rid of that subscript A. In general, if the equilibrium dissociation constant is less than 1, equilibrium is shifted left. That means anything that's on the right side is shifting left, so therefore must be stronger. So if K is less than 1, the conjugates are stronger than the Bronsted-Lowrys. If K is greater than 1, the Bronsted-Lowrys are stronger than the conjugates. And obviously, if K is equal to 1, then the Bronsted-Lowrys are equal to the conjugates. Okay. And that's how we know if we have a strong system. Typically, so these are all good bullet points here. Another bullet point I'll put down here. If K is greater than 1, whatever the argument is, which is always going to be a Bronsted-Lowry, whether it be acid or base, we say it's strong. It's a strong electrolyte, strong acid, strong base, what have you. If K is less than 1, we would start using language of weakness. So the Bronsted-Lowry is weak with an 8. Okay, so there's some good stuff there. Okay, so pause the video, have a perusal. Meanwhile, we will plod on. Okay, only a few more pages in this video left. And again, these notes have already been posted for the benefit of my students. In a typical general chemistry class, which this is geared towards, we just look at an aqueous environment. Although we can have environments other than aqueous environments. So for example, here we've got ammonia gas and HCl gas to give ammonium chloride solid. And some of you might have done this experiment where you essentially open some concentrated ammonia, open some concentrated HCl, and just allow the gases to mix, and you see a white precipitate form. It's one of the ways you can measure, quantify Graham's law of effusion. You can do it inside a tube and then measure where in the tube it happens. It's kind of cool if ever you get a chance to do that. So here we can see that HCl donates its proton. We know that HCl, although HCl gas is actually not an acid, it has the ability to donate its proton and produce an acid in an aqueous environment. So whether we call it acidic or not, it can definitely dissociate to produce H plus given the opportunity. NH3, we know, has a lone pair on nitrogen. And so we can have the unity of the H plus with the NH3 to give NH4 plus, which would then form an ionic compound with Cl minus. Here, because HCl donated its proton, we can still call it a Bronsted-Lowry acid, and ammonia, NH3, is accepting that proton, so we can call it a Bronsted-Lowry base. So you can still do your donate, although it won't be the main type of acid-base theory we'll see in a general chemistry class. You can definitely do things out of an aqueous environment. Okay, moving on to the third of 3 acid-base definitions we'll see. This is the Lewis definition after Gilbert Newton Lewis of Lewis structure fame, around the same time as the Bronsted-Lowry idea. So these were all within like a decade of each other, around 1910 for the Arrhenius theory, early 1920s for both Bronsted-Lowry and the Lewis theories. So remember that we said, so just to compare it with the Bronsted definition, remember a Bronsted-Lowry base is a proton acceptor, just like ammonia was here. So this essentially is looking at the chemistry up here as an example. The proton from the HCl was mopped up by the lone pair of ammonia, and we formed the ammonium cation. You can reinterpret this from Lewis's perspective. A Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. So ammonia in this example has an electron pair, and it donates them to H+. H+ in this example has space for an electron pair, so it will accept them. So here the H+ is acting like a Lewis acid, and the ammonia is acting like a Lewis base. So it stands to reason that Bronsted-Lowry acids and bases also fulfill the Lewis definition, but not the return favor. Not all Lewis definitions fulfill the other. Because Lewis acids and bases can be things other than proton donors. You know, we can go beyond proton chemistry with the Lewis definition. And so you'll find the Lewis theory is a lot more common, a lot more practical in aprotic environments or environments without protons. So let's write that down. So most useful in aprotic environments. I don't mean it's not useful anywhere else, but its useful becomes definitely more unique because of its ability to handle aprotic or non-aqueous environments. Okay. Okay, so let's see how they differ. So, you know, if you look at these bullet points here, the real difference isn't apparent here, but until you get to this last bullet point, the Lewis way of thinking is we form coordinate covalent bonds, which would produce the product, a Lewis adduct. So as you might see from the word adduct, it's literally two things added together to make one thing. So a Lewis base is a proton, is an electron pair donor. So when you donate a pair of electrons, and then you've got the acid which accepts them, you form a new bond. You form specifically a coordinate bond. Coordinate means that both of the electrons come from the same atom rather than being shared in a regular coordinate, in a regular covalent bond. So again, coordinate means they both come from the same same source. So both electrons from same atom from the donor, right? Okay, so let's have a look. Let's clear that and scroll. So here's some adducts. So here we've got the Lewis acid A, the Lewis base B with its lone pair, and then we can form the coordinate bond. We can form the Lewis adduct, which is the structure, but the coordinate bond is the bond that actually forms the adduct. So this is the coordinate covalent bond that produces the adduct. And you can see examples of this would be BF3 and ammonia. BF3 is stable, but it's got a deficit of electrons. It's only got, it doesn't have a full valence shell around boron. So it's able to accept an extra lone pair. And ammonia has a lone pair. So we form the coordinate bond, but remember that both electrons in the bond come from the same source, nitrogen. So we form our adduct, and we have our coordinate bond. So clearly the Bronsted-Lowry definition wouldn't apply here because we don't have any protons being donated or accepted anywhere. Okay. Other examples of Lewis acids, well, the easiest ones are anything that can accept electrons will be cations, right? So all cations can be considered Lewis acids. Not all cations are equally capable of being a Lewis acid, but they have the ability to accept electrons at least. We can have things like BF3 that have fewer than a full valence shell. So for example, AlF3, we have fewer than 8 electrons around the central atom. We can have things like SiBr4 or SiF4, which have more than 8 electrons, or have the ability to have more than 8 electrons around. So AlF3 has fewer than 8 electrons around its central atom. Silicon tetrabromide and silicon tetrafluoride, they have 8 right now, but silicon is capable of expanding its octet, so it's capable of having more than 8. So either way, these species can accept, they can serve as Lewis acids by accepting a coordinate bond, and obviously cations can accept a lone pair of electrons. This is just a repeat of this up here for some reason. Not sure why it's repeated. And again, the nice thing about Lewis theory is it doesn't matter what the phase is, whether it's solid, liquid, or gas. Certainly, you don't need an aqueous environment. So this makes it very versatile. We can form coordinate obviously, if you form a coordinate bond, you can form coordinate compounds. We actually won't look at coordinate compounds specifically just yet. We will look a little bit at coordinate compounds insofar as the acidity of them. But just to remind my students that we look at coordination compounds much later on in our course. And if we mention them briefly here, it's not to exhaustively look at them, it's just to mention them in terms of their acidity. So having said that, let's skip this coordinate compound, which is this hexa-aqua ion here. Let's go right to CO2. So carbon dioxide can form a Lewis adduct, which is carbonic acid. And we can see that from its resonance. So if you take CO2 here, then one of its resonance forms could be this redistributed form here, where the lone pair can push electron density towards an extreme oxygen atom and form this temporary separated charge. This then allows a water molecule, so OH2 here, the lone pair on the oxygen, can now attack this electron deficient region, and we can form carbonic acid. So you can see here that, I don't know how clear it is to see, so maybe I'll try and make it a bit clearer, just in case it's not. If we imagine we have the water here, so this is the water molecule I'm trying to talk about here. Then if we form a bond here, then we can have like a little wraparound here. So the lone pair can hit here. This negative charge can attack here and break this bond. So we get an OH, which is over here. And we obviously get an OH, which is on the carbon. So we get carbonic acid, which is H2CO3. carbonic acid, which could be acid rain, you know, in our atmosphere that's forever being pumped full of CO2. Carbonic acid is also for any medically inclined people in the class. That's how we transport CO2 around our bodies. We don't bubble CO2 through our veins. We transport carbonic acid through our veins, and then we can excrete the CO2 in our lungs, etc. Okay, let's have a little bit of a scroll. Carbonic acid would be written as a weak acid. So the predominant species would be H2CO3. The predominant species would not be anything other than that. Remember, anytime you have a weak system, keep it intact when you write it as an equation to represent its predominant species. Now, what do I want to see here? This is actually the last item on this video. This looks, let's see, is there anything new I want to see here? Not really. Not really. I think we've said everything that this is trying to say. So just that, you know, nitric acid here is shown, and water to give nitrate and hydronium. We can see graphically here that we don't have any reactants left. So it wouldn't make any sense to write HNO3 as the predominant species. So if you know you've got HNO3 and you know it does this, then you would just write NO3 minus and H3O plus. It makes no sense to write HNO3 because it doesn't exist. It's gone, it's separated. You don't have that anymore. The predominant species is what you would write. Okay, so that will wrap up this first acid-base theory video.